Do repeat. Okay, so look at 621 to 624. What's happening there?
This is being added by 3 is being added.
It's adding by 3? What about 624 to 625?
Only one has been
Adding 1. What about 625 to 624?
Only one has been subtracted.
Oh, we're subtracting 1. 624 to 621. So look here again. Is there a pattern with these teal numbers?
Yes.
What's happening to the 3 to go to that 1? Minus 2? 1 to minus 1? Negative 1 to negative 3? Oh. So it doesn't look like there's a pattern off of the surface, but is there? A little bit. By the way, I want us to look right here. Does anyone know what we would call this right here? It's constant something.
Constant something.
Constant additive. Remember, subtracting is just a form of addition, right? So this is constant additive right here. Notice I'm not calling it the rate of change because the rate of change is only that first column. But hey, what type of function had a constant additive rate of change?
Linear.
A linear function has a constant additive rate of change, right? So right here, this isn't a function, but it is some form of rate of change. Once again, what type of function had constant additive rate of change?
Linear.
Linear function. So what do you think we would call this rate of change?
Linear function.
Not a linear function, a linear rate of change. And really, I would also say linear additive. And so that's what we would want to notice. It's not a pattern right away. We don't see it immediately. But when you start to look at those differences, how much is being added or subtracted, and you go a little bit further, we get to constant additive. We know a linear function has a constant additive rate of change, so this would have to be a linear additive rate of change. So what type of rate of change does a quadratic function have? Quadratic functions have a linear, or have, I'll just leave it there, they have a linear additive rate of change. Nothing is random in mathematics. There's a pattern to everything. Every quadratic function you ever look at will have some linear additive rate of change. So we're going to look at another way to see this, with the other way to represent this in a table. So I worked with group 2 on a different method in the calculator. So make sure you have those notes that quadratic functions have a linear additive rate of change. And again, please note, you have to get to the constant additive to know what rate of change it is. The rate of change is only in this first set of differences. The rate of change is only in the first set of differences, but we can find that rate of change by finding where it becomes constant additive. So create another list and spreadsheets page in the calculator. I'll leave this information up here so you can take notes later, but create another list and spreadsheets page. I'm just going to call this base 1 because I need a different variable name. I think that'll work. Yeah. And I'm going to call this height 1. If you put the same exact variables in, it'll just fill it in for you. And I'm going to call this area 1 as well. This time we're going to go by 5s, okay? Just to give us a different look at it, but I'm also going to show you a different way to enter these functions to make your job easier. So base, what's the first base value I should type in? 0. And then you will need the recursive form. I'm going to go by 5, so equals 0 plus, or not 0, a1 plus 5. So get your base values in there. Make sure you stop around 50. I think you need to go to 11. So you need row 11 to get to 50 by 5s. So we're going by 5s this time. So start at that 0. But then use your recursive definition to add 5. What's your question? You always have to type in equals to do a formula,
You say 5.
right?
Answer.
Well, not just 5. Notice I wrote a formula. I took the previous value and added 5 to it.
Oh, plus 5.
Right, remember you take the A1 and you add 5. That previous number and you add 5 to it, creating that formula so you can drag and drop it. Who needs me to wait before I move on to the height section? You need to type it in the white cells, not the gray cells. You have to start with 0, and then you have to do that previous value. And what are you adding to that previous value? Right? And then you can drag and drop it.
How far are we going?
You need to go to row 11. Okay? That'll get you to a base value of 50. Alright, so now let's look at the height. Because what we've been doing by dragging and dropping is called recursion. You're taking the previous value and adding a certain amount to it each time. That's called recursion. But what's easier a lot of times than recursion is an idea of explicit. In an explicit, you can put in any input and immediately get the output. Well, what do we know about the base and the height? When I add them together, what do they have to add up to be? Just the base and the height. The base plus the height has to add up to be 50. Oh my goodness. Base plus height equals 50. Well, I already have a value for the base. So I want an equation where I could substitute the base value in and get the height out immediately, which means my base becomes the, I want to substitute in, so the base would become the input and the height would become my output. So how could I rewrite this equation so that my height is equal to something with my base? I need to rewrite this. Say again. So would b minus 50 work? Is that equivalent? Do I want to add on to or push back on that? Would it be 50 minus b? Well, stop just saying stuff. Use logic. Which one is it supposed to be? I want an equivalent form of base plus height equals 50 so that I know what the height is equal to every time. So which of these two? Can't be both. They're similar. Look at this equation, guys. I want to solve for this height.
It's the purple
This is an
one.
all call for anyone who has yet to have their picture
I want to
taken
solve
in the
for height.
yearbook. Come on
It's the
down to
purple
the
one.
theater, 9th through 11th
Say again?
graders, and any staff members.
It's the purple one? But how do we know it's the purple one?
This is the final all call. Thank you.
I need to subtract what? Oh, if I subtract b from here, b minus b is 0. Subtract b here, and I'm left with 50 minus b. So the height is equal to 50 minus whatever the base is. And so this is where you can actually go into the gray cells where it says equals. So if I come up here, I'm going to type in equals. Notice how it says height 1 equals, right? H equals. What do I need to type in there? The height is equal to 50 minus b, which is, I typed it in as base 1. Look at the beauty of that. It filled it all in for you. You type in that formula, 50 minus base 1, or base, whatever you put in there. And it immediately gives you the entire column of values. So if you can develop an explicit formula, it works really well for you. So you don't, If you use what?
The other
The,
one.
it just messes up. It would give you negative 50, negative 45, negative 40, right? Because it's going to take whatever the base value is and subtract 50 from it. Yes?
Could Max put 50 in the first height column and then do
Yeah.
50 1 minus 5?
Yeah, you can. And so, now, looking at the area, how are we going to calculate area? Jackson.
Base times height.
Okay, so notice I can explicitly say that area is equal to base times height, right? So I'm going to type in equals base 1 times height 1.
What equals base 1 times height?
Well, area is base times height, right? So I typed in my base, variable equals base 1 times height 1. So this is why you want to use full words, because if you use just single letters, it's going to ask you if it's a variable or column every time. It'll still work, but that's what it'll do. Now you need to be careful. You need to go back up here. You're going by 5s here, right? Oh, and that's why. So right here, notice how you title it base 1. So you need to actually use base 1 here. So let's delete. So minus and type in base 1. And then when you go here to area 1, you need to type out base 1 times height 1. Okay.
Is this her calculator?
That's mine. So you can leave that there. That's her book though, and everything else is hers. Okay. So once again, let's look at the evidence.
Teachers, excuse this interruption. We need any juniors with the last name.
Do we see evidence that 625, 25 by 25 is the biggest area? We got 15 minutes of learning, good learning.
If they hold for juniors.
Which juniors?
Something.
Yeah, definitely.
Yeah. Go quickly, we got stuff to learn.
Yeah, read off one now,
Yeah.
yeah, I left it in my Spanish class.
Wait, you all said T through G? So AJ, that wouldn't be you yet.
It's in your
Yeah.
what is her phone?
T through Z.
Is
Q comes before that.
oh.
Oh, which one's JC? JC is.
No, I was at football.
You get hard.
I mean, you can go and go. Already is what they said.
I was at football though for a few.
That's what they called it yesterday. I think they're still calling though all the different names, but you can go and go. We're just going to continue. Okay. So do we still see evidence that 25 by 25 gives us the largest area?
Just me and my boy over here.
Wait, why are you going?
This is my Aunt Harris.
They T through Z doesn't include H. Anyways, I will once again point this out. If I'm looking at this quadratic function, do I see a linear additive rate of change? So plus 75 plus 25 minus 25 minus 75. So to go from 75 to 25, subtracting 50 minus 50 minus 50. That's what? Constant. Well, notice that's constant additive. So this rate of change is linear additive. Constant additive on that second set. So the first one, the rate of change is my linear additive rate of change. Right? So anytime I see constant additive, I know what came before it is linear. And so it would be a linear additive rate of change. Negative 25 to negative 75 is only minus 50. You were thinking positive 25 to negative 75. Okay, so we still see that evidence there. And so once again in a table, we can see the what for that function? The rate of change, thank you. But what other representations do we still need to look at? Graphs and algebraic, those equations.
Right.
So we can actually use this information right here to help us significantly in getting an equation. Notice how we said area is equal to base times height? How many variables do we want though?
One.
Just one. But I've already found out that the height is equal to 50 minus the base. So what could I substitute 50 minus the base in for?
H.
H. See how it's equal to the height? So that 50 minus the base can be substituted in for height. And so now the area is equal to B times what?
50 minus. 50 minus.
Is that correct? Is that what the height is? This is something you would want to put under extra notes. This is known, see how these two different things are being multiplied by each other? This is known as the factored form of quadratics, or quadratic functions, quadratic equations. This is the factored form of quadratic equations, huh? I'm sorry. The thing that you would want to notice about that is, if you were to just look at the b, the base, what type of function, right, if I were to type in the equation y equals b, what type of function would that be? Why not? It's one we've already studied. We'll point this out as the same as 1 times the base plus 0.
Is there a slope intercept?
That's linear. It's the slope-intercept form of a line, right? So that's linear. 50 minus b, that would also be linear. You can switch around. Negative b plus 50, it's got a slope and a y-intercept. So when we look at the factored form of quadratics, it's the product of what two types of functions? Linear. A quadratic function is the product of two linear functions. This is something that's going to show up throughout this unit and in the next unit. So you need to pay attention to this detail. Product of two linear functions. When it comes to quadratics, we are going to look at 3 different forms. That's one of the main ones. That's what we're going to use to define a system known as the polynomial functions. We can also see one of the other forms really quickly. What property can I use to multiply this b times everything? Distributive. So what is b times 50? 50b minus, remember that would be b times b, and so it's not b plus b. Remember, when you repeatedly add, you end up multiplying. b plus b is 2b. b times b, repeated multiplication, is an exponent, b squared. Traditionally, we would write this as negative b squared plus 50b, because you start with the highest exponent and go down. You descend in the exponents. This, if you add a 0, is known as the standard form. Remember, these are notes to refer back to later. You don't have to know all of this right away. This is so that you can refer back to this as we move through the unit. Standard form of quadratics. When you have a standard form of a quadratic, what should jump out at us? What's unique to this quadratic that we didn't see in linear or exponential?
2 variables.
Yes, it is a little bit longer. What?
2 variables.
Is it 2 different variables? It's the same variable. It's still b. But what exponent do we have in a quadratic?
A variable for an exponent.
Not with a quadratic. That exponent's not a variable. What's the highest exponent? 2. The highest power in a quadratic is the second power. So in standard form, the highest power is the second power. Okay? So when we have that standard form of quadratic, we would want to note that the highest power is the second power. So last thing that we're going to look at is the graph. Create a graph page with me so that you can learn how to do this. Alright, so we need to open a graph page. So Control Doc, add a graphs page. Madison, do you have that calculator in hand so you can do this?
Sorry.
Now, once you have a graph page, we want to graph the individual points, and when you create a list in spreadsheets, you can do that. So so what button are we going to press to be able to do things on this calculator? Menu, okay? We want to create a what? A graph. So we're going to go to graph entry / edit. Do not go to function, because what you want is to graph those individual points from a list. So we want a scatter plot. Thank you. So we go to scatter plot. And so you're going to see S1. What you can do in this calculator once you have the scatter plot, right above the number 9, what do you see there? On the calculator, above the number 9, what do you see?
Variable.
That's VAR for variable. So click on VAR and put your variables in. My X variable, I'm going to use just base
Wait,
is
how
going to
do
be
you
my
get all
X.
How do you get all those options?
You hit VA, well, if you had to put your variables in earlier.
Yeah, I did.
Yeah. So notice I did area and area 1 based on those two different lists and spreadsheets. I did base and base 1. Okay, so I'm going to make my independent variable base. What's the dependent variable, the output that I want?
Height?
But remember, height is what we had to use, but what's my dependent in the equation? I want area, right? So I've got base and I've got area. You need the corresponding ones. And I'm going to hit enter. I only see 1 point. Anyone know why? Think about the values in that table. The height, or the base, goes all the way up to 50, doesn't it? Look at the area, it goes all the way up to 625. Can I see that in my current window? So I need to do a thing in the calculator again. So what button am I going to press?
Menu.
Menu. Where am I going to go to change? Huh? Not view, look again. Look again.
4.
Windows / zoom. I want to change my window. The view is not a bad option to think about, but I want to change my window. Specifically, when you have scatter plots, go to zoom data. It's going to zoom right in to your data. Yeah. Is that pretty good evidence that 25 by 25, that little maximum up there, is my biggest area? Because you didn't hit, you have to hit Windows / zoom, and you need zoom data number 9. Then you didn't put,
So basically,
I have no idea, I'm going to have to look at that more heavily. But something happened when you did zoom data. For some reason, it's only putting 2 points in one. I'm going to look at it more heavily. Okay, so now we can put in the function. And I'm going to just do this quickly. You don't need to, but I do want you to see function what do we do? Negative b squared plus 50b? Or negative x, hey, stop, backing. Plus 50x. You see how every single point is on that curve, on that function there? Remember, the whole point is that each of those points, Key Anthony, will make that equation true. Now, the last thing I want to point out is this. This shape, this is my graphical representation. Does anyone know what this shape is called? It's called a parabola. The shape of a quadratic is called a parabola. Either it's called concave, we already talked about this, concave down, or it can be concave up. So, quadratics have parabolic shapes. There's the bell. Sorry, we're a little bit over, but that is it for the Gold Rush task. Tomorrow we will use the book. Make sure you have that with you. Hey, it says no homework assignment. Instead of that, I need you to complete that Venn diagram. The Venn diagram where you're looking at what's just linear, what's just exponential, that's where we're starting class tomorrow. You need to have your Venn diagram completely done. I will include that in the slides when I upload them on the Schoology. So, complete Venn diagram. By the way, I won't see y'all tomorrow. You got the ACT test. So y'all need to have this done before Friday. So complete that Venn diagram.
Dude, I got a whole thing. Bro, I'm fixing stuff up for her.
Well, it's more about what's more useful long term. So if you look, and that's so one of the groups. What's up, Peyton?
I'm being a nice gentleman. I'm being a nice gentleman.
Don't do that. I'll look for it, but don't throw it away. It's all 0. I think your grade's still an A, isn't it? Or is it a B?
It's like a B, but still, I need to get rid of it.
I'll look for it. I'll look for it. So if you look at a parallelogram, you can't do length times width, but you can take the base and multiply it by the height. That's also why the area of a triangle is 1/2 base times height. You look at a trapezoid. What is happening with a trapezoid is that, let's say I find that mid segment right here, right? That triangle perfectly fits into there, and that triangle perfectly fits into there, creating again a rectangle, so base times height, and that even carries over into volume. And so you take the area of the base and you multiply by the height. So it's the transferable principle.
No, I definitely get why you said that.
Yeah.
I'm just like,
In the context of length times width, and I get that. I just want transferable principles. I want students to recognize that one strategy, one way of thinking about it will help, and you can translate it to base times height. Yes, it is length times width in terms of if we're measuring in the real world, we would typically call it length times width. But it's that, again, I just always want to focus on a transferable principle. Man, a lot of those students are still